Today I'm going to talk about the Cobweb model, which is a model in macroeconomics, and one of its main characteristics is that it's a dynamic model. By dynamic, we simply mean that the model tries to get to the equilibrium over time. So by dynamic, we simply mean time. In economics, we sort of use models to answer a specific question, and here's the same. The Cobweb model tries to answer a specific question in economics, and that question is that suppose we have a simple supply and demand model, a quantity on the horizontal axis and P on the vertical axis, and this is the supply curve and this is the demand curve, and here is the equilibrium point. Now, the question that the Cobweb model tries to answer is that suppose we're off the equilibrium point, like suppose we're here. The question is that how are we supposed to get into this equilibrium point? Are we supposed to go like this, or like this, or like this? This is a good question, and to answer this, we need a model. The reason that we call this a Cobweb model is that the way that we sort of get to this equilibrium point is looking like this, which is like a cobweb, and this is why we call it a Cobweb model. So we sort of converge over time into this equilibrium point. To start about this model, we start with the equilibrium point. At equilibrium, we have supply equal to demand. Please pay attention that the variables have the subscript of t, which means that the model is dynamic, as I said before. So what's st? St is equal to alpha 1, which is intercept. Here we have intercept, plus beta 1 times pt minus 1. It means that the quantity supplied is determined by the last period's price, and beta 1 is just the slope of the supply curve, and beta 1 is bigger than 0 because the supply curve is upward sloping. So what's dt? dt is equal to alpha 2, we have intercept here, plus beta 2 times pt, which means that the quantity demanded is dependent on the price of this period, and beta 2 is the slope of the demand curve, which is negative because the demand curve is downward sloping. So the left hand side of these equations are equal to each other, as we said here. So the right hand side of these two equations can be also equal to each other. So we have here, as we said, st is equal to dt. So alpha 1, the right hand side are also equal to each other. Alpha 1 plus beta 1 times pt minus 1 is equal to alpha 2 plus beta 2 times pt. And we call this equation number 1. In equilibrium, we sort of have the price of the next period, pt plus 1, being equal to the price at this period, which is pt, being equal to the price at the last period, which is pt minus 1. These prices are all the same because we are in equilibrium, so we can simply call them p bar. And in equation 1, we said that we are in equilibrium because the quantity supplied is equal to the quantity demanded. So we can simply plug p bar into equation 1. And here we have alpha 1 plus beta 1 p bar equals to alpha 2 plus beta 2 p bar. And we call this equation number 2. So now we're going to subtract equation 1 from equation 2. Equation 2 minus equation 1. And we have alpha 1 plus beta 1 p bar minus alpha 1 minus beta 1 pt minus 1. equals to alpha 2 plus beta 2 p bar minus alpha 2 minus beta 2 pt. And alphas are just cancelling out, and then we can simply, and the betas can factor out of the equation. So we have beta 1, sorry, let me put it here, beta 1 times p bar minus pt minus 1 equals to beta 2 times p bar minus pt. This is a very important equation, and we call it equation number 3. So I'm just gonna copy this equation here. So we have it here. So as I said, this is equation number 3. And from this equation, we're going to discuss about convergence and divergence. Now, we can solve this equation in 2 ways. The first way, we call it A, is that we actually want the price at period t to go to the equilibrium price. So we solve for pt. So here we have p bar minus pt equals to beta 1 over beta 2 times p bar minus pt minus 1. So, and then we solve for pt, and we have p bar plus beta 1 over beta 2 times pt minus 1 minus p bar. And this equation is the general solution for the Cobweb model. So this is general solution. Sorry for that, solution for a Cobweb model, and we call it equation number 4. And what's this equation telling us is that for the price at period t to converge to the equilibrium price, which is p bar, we just need this second part of this equation to get to 0. So we need this second part to converge to 0 over time, so that we can get closer and closer to p bar over time. And this is the idea of convergence. So that's it. And now we're going to talk about the another way that we're going to solve equation number 3. In the second way, we we suppose that we call this part p hat t minus 1, and we call this part p hat t. And here we have beta 1. We just actually use p hat t minus 1 instead of this part. So beta 1 times p hat t minus 1 equals to beta 2 times p hat t. And as I said, we solve for p hat t because we want the price at period t to go to the equilibrium price. So we have p hat t equals to beta 1 over beta 2 and times p hat t minus 1. This is a very important equation, and we're going to discuss convergence and divergence of this equation. So for simplicity, we just simply call this part A, and then we have p hat t is equal to A times p hat t minus 1. And the general form is that p hat t is equal to A to t times p hat 0. So this is a very important equation. And if you pay attention, you can see that equation 5 is just the same as equation 4. It's just in another format. so that we can actually discuss convergence and divergence more easily. And the reason that we can put this equation into this one is that, for example, p hat we want p hat for period 1. We have a times p hat for period 0, and the next period is p hat 2, which is a times p hat 1, and we already have p hat 1 here, so we can plug it in here, and we have this one, a times p hat 0, so it's going to be a to the power 2 times p hat 0, and this is why we call it this way. So for now we're done with the equations. Now we're going to discuss convergence and divergence, but before that I'm gonna discuss about slopes of the curves and functions, which we're going to need for divergence and convergence. So as we said, A is equal to beta 1 over beta 2, and the supply and in the supply and demand curve function we had alpha 1 plus beta 1 times pt minus 1. So beta 1 is simply the slope of the supply function, and the beta 2 is the slope of the demand function. But when it comes to the actually graphical model, here we had Q, and here we have P, price, and this is the supply and this is the demand. Please pay attention that in the graphical model we have the actually dependent variable on the vertical axis, dependent variable, which is P, price. But in the equations we have quantity as a dependent variable, so it's sort of reciprocal to each other. And this is why the slope of the supply and demand curve is reciprocal to the slope of the supply and demand function. So here is the slope, or let me write it here, the slope are beta 1 and beta 2, but here the slope is simply 1 over beta 1 for the supply curve and 1 over beta 2 for the demand curve. So please pay attention to this topic because we're going to need that. Now I'm going to talk about convergence and divergence. And as I said, for convergence and divergence, we just all we need is equation 5. So I'm going to write it here again. Equation number 5 was p hat t is equal to a to the power of t times p hat 0. And we said that a is equal to beta 1 over beta 2. So we're going to talk about convergence. This equation simply means that for convergence all we need is that the right hand side of the equation goes to 0. So for this part to get to 0, we simply need a to be less than 1, because that way it just gets lower and lower because it gets the power of t. So for a to be lower than 1, all we need is the numerator to be lower than the denominator. So for convergence, beta 1 should be lower than beta 2. In that way, a is going to be less than 1. So in t periods, a is going to get lower and lower until it converges to 0. So this is the convergence situation. And on the graphical model for convergence, all we need is the slope of the supply curve to be greater than the slope of the demand curve, because here we had the slope of the supply function being lower than the slope of the demand function. So for the curves, it's just reciprocal of that. it's like this. 1 over beta 1 is the slope of the supply curve, should be bigger than the slope of the demand curve, which is 1 over beta 2. And now we're going to show this on graph. Here is quantity and this is P. So the slope of the supply curve should look something like this, and the demand curve should be, I guess, something like this. This is demand. So now we're off the equilibrium point, like here, and we see that we can simply converge to the equilibrium point. And the reason that we converge to the equilibrium point is just because the slope of the supply curve is bigger than the slope of the demand curve. So this is the convergence. So all we need for convergence is the slope of the supply function to be bigger than the slope of the demand. The slope of the supply curve to be bigger than the slope of the demand curve. So it's a very important point. Now we're going to discuss about divergence. As I said, in equation 5, all we need for divergence and convergence is that the right-hand side of the equation goes to 0. So for divergence, the right-hand side shouldn't go to 0. So for this part not going to 0, all we need is that a should be bigger than 1. So for a to be bigger than 1, we need that the numerator being greater than the denominator, which is beta 2. So in this way, a is going to be bigger than 1, and in t periods, a won't converge to 0 because it just gets bigger and bigger. And these are the supply and demand functions, the slope of the functions. So for the curves, it's just a reciprocal, so that the 1 over beta 2 is the slope of the supply curve should be lower than the slope of the demand curve. And this is the situation that we diverge from the equilibrium point. So on the graphical model, we have quantity here, and this is price. So for divergence, we need the demand curve to be much should have more slope than the demand curve, than the supply curve. Sorry. So this is supply and this is demand. And we are off the equilibrium point. For example, we're here, and we can see that we won't converge to the equilibrium point. We're just getting further and further away. So we're not going to converge. So as you see here, the slope of the demand curve is bigger than the slope of the supply curve. So we won't converge to the equilibrium point. But here we had the slope of the supply curve being bigger than the slope of the demand curve, so we simply converge to the equilibrium point. So all we need for convergence and divergence is the slope of the curves. So please pay attention. And the last topic I'm going to talk about is that how we're going to actually converge. How we converge. As I said before, A is equal to beta 1 over beta 2. And beta 1 is positive because it's the slope of the supply function, and beta 2 is negative because it's the slope of the demand function. So this simply means that A is negative because one of these actually is negative. So this is negative and this is positive, so the whole thing is going to be negative. And the question here is that what's the sign of a to the power of t? Is it positive or negative? It depends on t. If t is an odd period, then it's definitely negative. If t is an even period, then it's definitely going to be positive. So this simply means that for one period, for example, we start from period 0, which is even, we are above the equilibrium price, and for the next period, which is 1, is odd, we are lower than the equilibrium price. So it just simply means that we oscillate above and below the equilibrium price, and we can simply show it like this. This is t, and this is period 0, for example, period 1, 2, 3, 4, etc. And this is p, and here is the equilibrium price, p bar. So the way that we converge to this price is something like this. For period 0, we are above the equilibrium price, and for period 1, we're below this, and for the next period, we're again above equilibrium price, and then we get lower, and then above, and then below, and we see that we're just getting closer and closer to this point until we converge to equilibrium price. So this is the way that we converge to the equilibrium price. And the way that in slide 1 we said that here we are above equilibrium price, and then we get to the and here we are below equilibrium price, and just over time we just get closer and closer to the equilibrium price, and simply it means that we oscillate above and below the equilibrium price, and over time we just get closer to this. So we can show this thing into this graph, which is way more easier to understand. So another thing to pay attention to is that the reason that we oscillate like this is because the slope of the actual demand curve is negative. The slope of the demand curve being negative is what's actually caused A to get to be negative. So that's why we oscillate like this. If beta 2 was positive, then A would be positive, and we wouldn't be actually oscillating like this. So this is all about Cobweb model. I hope you enjoyed it. Please, for more videos, check out our website, www.rasoboost.com. I hope you can find more videos there. Thank you and have a nice day.